Okay, this is just a test. You plug in 0 for x, and that will come to 3. Plug in 1 for x. Sorry, up here, let's erase that really quick. Start off with the correct numbers. Plug in a 0, and that will come a 1. Plug in a 1, and that will come a 3. Plug in a 2, and that will come a 9. Okay, this is your Algebra 2 Chapter 8 sample test, and I'm going to try and run through this, and I'm using new software, so I have no idea how it's going to work, but we'll find out. General form of an exponential equation, so we have y equals ab to the x power. Question is restrictions on b, and the only thing, we've covered this in class several times, but b has got to be greater than 0. It can't be 0 because 0 to the x power, no matter what x is going to give you a 0. And we said b can also not equal 1 because you just raise 1 to the x power, you just keep getting 1 back. So those are restrictions. And you should note then the inverse of exponentials are the logarithms. So log base b of x. And what this tells us, see if I can undo that line there real quick. Nope. What this tells us is on the b value in a logarithm, it has those same restrictions since it's the inverse. So your b value has to be greater than 0 and cannot equal 1 for a base. My car in problem 2 depreciates by 15% each year, and here's the original price of my car. So this is an exponential function. Each year I only get 85% of my car back. So we said in class you calculate b as 1 plus your rate of return. In this case, my rate of return is minus 0.15, and so b is going to be 0.85. And so the general equation, it's actually down here in C, which I think is a good calculator. Determined first is my car starts at $25,000, and I get 0.85 of it for every t years that go by. So after 1 year, I get whatever 25,000 times 0.85 to the 1 power is, or 0.85. After 2 years, it would be 0.85, and then 0.85 of that. So that's what the exponential does. Alright, let's slide this up now. Alright, problem 3, we've got some Mr. Todium 44, and it has a half-life of 6 days. We start with 70 kilograms, and we're supposed to write the equation. This is a half-life problem, and we gave you a formula for that in class, but let's see if we can reason it out. The amount I end up with is going to be based off of how much I start with, which is 70 kilograms. This time, every time a half-life goes by, it gets cut in half, so I want this growth factor to be a half right in there. And then I want my exponent to count the number of half-lives that go by, so it's t over 6. So when t is 6 days, 1 half-life has gone by, and I'd get a half times 70, which gives me 35. So this would calculate exactly how much I have after time t, where t is in units of days. Problem 4 is a little bit tougher. In problem 4, we ask, use the equation you just found out to determine how long it takes for 5 kilograms of Mr. Todium to remain. So we end up with 5. We start with 70, 1/2 t to the 6th power. I don't have my calculator here, so I'm just going to show you the steps that you'd use. I want to solve this thing for an exponent, and logarithms are explicitly used for finding exponents. Now, I want to get the factor here that has the exponent alone, so I'm going to divide away the 70. So you divide both sides by 70 here, and that's going to reduce to 1 over, what's that going to be, 14, I believe, equals 1/2 raised to the t over 6 power. At this point we're going to log both sides. So I'll just write log in here, and you'd use any base, but it'd be wise to use a base 10 since our calculator can deal with that. And so I've got log of 1/14 equals, my exponent pops down, log of a half. Okay, and we've done problems similar to this before. Let me erase a little bit of our stuff we've got here. We've got plenty of room. We've done this before, and we're just trying to solve this for the variable t right here. And so to solve for the variable t, we're going to divide away the log half. And so now I'm at t over 6 equals log of 1/14 over log of a half. And then finally we multiply by 6. And so your final answer is just going to be, if we can get this to work for us, erase not all of that. I just want to erase a part of that. Not going to do it. So we'll squeeze it in here. Our final answer is going to be t equals, taking both sides times 6, log 1/14 over log of a half. And at this point you would just get out your calculator and you could type that in, and it would tell you how much time has to pass for the 70 kilograms I started with to leave only 5 kilograms of clearly radioactive Mr. Todium remaining. Alright, let's slide up here a little bit more. Alright, now we just have to evaluate a few logarithms. So go back to the definition of what a log says. This one has a base of 3 on it, and so we'd write 3 to what power gives me 3. Answer, clearly 1. 3 to the first is 3. 6 is saying 3 to what power gives me 9. Clearly that's a 2. Third one says 3 to what power gives me 27. Clearly a 3. Next one says 3 to what power gives me a 30. I have absolutely no idea what that is. I know 3 to the third gives me 27, 3 to the fourth gives me 81, so it's going to be 3 point something. Over here it says to approximate it, so I'd get out my calculator and I'd do it. Now, some of you have calculators that do change a base for you, so you can just type in log base 3 of 30. For those who don't have calculators that do that, we use the change of base formula. And we're going to change it to base 10, so I just write log, and it's the log of the big number over the log of the little number, the former base. And so this would calculate the exact same thing as log base 3 of 30. But now I've done it base 10. And we could even show that base in there if you want to see that base in there. But we've just converted it to a base 10 logarithm. And that we can plug into our calculator. All of us can, because we do have calculators that are base 10. Alright, number 9 is asking 3 to what power gives me 1/3. Some of us may know this off the top of our head, but I would certainly not mind if you said, well, 1/3 is the same as 3 to the negative 1, and now that the bases are the same, we can see the exponent needs to be a negative 1. Okay, we are on page 2 now. I'm going to blow this up a little bit, see if it writes a little bit nicer. Same type of problem. 3 to what power gives me 1/9. Again, I'd get common bases, so I'd write that as 1/3 squared. I'd write that 1/3 squared is 3 to the negative 2. Bases are the same, so exponents must be equal. Problem 11. I write 3 to what power gives me negative 3, and right away I go, oh, something's wrong here. I can't raise 3 to any power to get a negative 3. In fact, inside a logarithm, you can never take a negative value. So this one, undetermined or not possible. Let's look at number 12. Number 12 says 9 to what power gives me 3. I'm going to write this as 3 to the 2x if I can. Let me erase that real quick. 3 to the 2x equals 3. The exponent on the 3 on the right is just a 1, so 2x equals 1, which tells me x is a half. And this should make sense because 9 to the half power means the square root of 9. Square root of 9 is 3. 14 we've discussed a little bit at the beginning of this paper, or this handout. We said, hey, that b down there, that base of the logarithm can never be negative. So again, this one's not even possible. 15, we don't give a base. That implies it's a base 10. So 10 to what power gives me 100,000. There's a couple ways to do this. The easy way is to say, well, when you multiply tens, you just keep adding zeros, and here we've got 5 of them all together. So this must be 10 to the 5th gives me 100,000, so that's just 5. Number 17, this is a natural logarithm. Okay, the natural log we're asking of 4. So e to what power gives me 4 is what that's asking. I don't know what that is, and so I'm going to have to grab my calculator. Just type in natural log of 4, and you'll have your answer. Number 18, we have to rewrite an exponential as a logarithm. So we're going to say x equals log base, look at the base there, it's a base of a of y. Okay, and if you want to just double check it, remember what logarithms say. This thing says a to what power, which is the answer of a logarithm, gives you y. So x equals log base a of y. Rewrite this logarithm as an exponential. This says b to the k power equals h. Your base b, your exponent is what a logarithm equals. For the following problems, A through F, use the given information and the laws of logs. Alright, I don't have my calculator again, so at least I'll get them set up for you. It's base 5, so every logarithm we write is going to be base 5 here. So if I forget, don't panic, just realize they are all base 5s. And I have to rewrite them as 12s and 20s, because those are the logarithms I know. So for example, I would rewrite this one as log base 5 of 12 times 20, because that equals 240. And then the law of logs says that's 12, log 12 plus log of 20. Okay, now we aren't done here. We'd then get out our calculator and we'd look up, hey, what's the log base 5 of 12? Well, I have it here, so that's 1.544. And I'd have to add that to the log base 5 of 20, 1.861. So your final answer is whatever that adds up to, 3.405, something like that. Okay, so that's our goal. Again, 12s and 20s. So this next one here, we don't have a 12, we don't have a 20, but that fraction unreduces or scales to, if I multiply by 4 over 4, to 12 over 20. And so now I've got a division, so I can write it as a subtraction problem. Then I'd pull those values from the top, the given information up here, and I can give a decimal answer for that. Number 5, a little bit tougher. We're going to get a little creative here. I'm going to write this as log base 5 of 5 times 12, because that equals 60. That's log base 5 of 5 plus log base 5 of 12. Now, log base 5 of 12 I know from the above, and log base 5 of 5 I also know because it's going to just be 1. 5 to what power gives me 5. So we can use the information that we know to determine it. And we certainly know log base 5 of 5. Several ways to do this next one. I'm going to do it as follows. That's log base 5 of 1 over 12 squared. And that's log base 5 of 12 to the negative 2. The negative 2 now pops out front because it's an exponent. And so that's just negative 2 times whatever the log base 5 of 12 is. And that's a value we have up above in the given information. Now we're into solving exponential equations. We log both sides using base 10. And the x pops out, and we divide by log 5. So our answer is going to be whatever this calculates to. This is calculator ready form, and then we can actually calculate it with a decimal. Next one's a base e, so we natural log both sides. It makes it clean up a little bit better. The x pops out. The natural log of e is 1, so we can just rewrite ln e as 1. So I get x equals the ln of 6, which again our calculator can perform for us. 23 is a logarithm. It says the base of 10 to the third power is x, so x is 1,000. 24, e to the x equals 1. You could rewrite this as a logarithm, or you could natural log both sides, or you could just realize x has to be 0. And then 25, the last one, we'll squeeze it in here, says e to the third power equals x. And so that's what x is. And you can grab your calculator and get a decimal answer for that if needed. And that's it. Hope this works.